Okay. All right. So let's start off first by drawing the problem. So I'm going to go ahead and start drawing this problem here. Again, this will be the deadlock detection algorithm. So let's write it here, deadlock detection. Okay. So I'm going to go ahead and start off by writing these two formulas. These are going to be important for you to know, is that R is equal to V plus A. And then, of course, if they give you, you might need to rearrange that. I'm not going to give you the other one because you can figure the other one out, and that'll make sense here in a second. But R is equal to V plus A, and this will make sense here in a second. So with deadlock detection, you're going to get a specific amount of matrices, right? So you're going to get a Q matrix, and this is called the request matrix. This is the resources that the computer is going to be requesting. Okay, and this will be important because this is kind of what you're basing everything off of. And this is called the allocation matrix A, and this allocation matrix is going to be the resources that the request matrix is actually going to allocate in the CPU. Okay, so I'll draw this out here. Actually, I'm going to make this a little thing here. Okay. All right. Okay. And then they're going to give you two things. They're going to either give you R or they're going to give you V. Okay. In this case, I'm going to give you V. So I'm going to give you V, and V is going to be equal to, let's see, in this case, it's going to be 102. Okay. R is equal to V plus A, so we can do is if we need the resource vector, this is going to be a vector that we're going to be using when we're comparing. Okay, so basically what's going to happen is we could take R, and again, R is a vector that is going to be used when we compare things. And in this case, R can be, well, I guess technically we're not going to be using R. R is only mainly used to find V, really. So I guess we don't really need R, but this is the formula you're going to want to write down for your extra credit tomorrow. It's just this here, okay? Because he might give you V, he might give you R, so just use this and figure out whichever one he gives you. But the one you're going to be using is V, okay? So sorry to confuse you there. Okay, so let's go over actually how to solve these algorithms. So first off, understanding what a deadlock is specifically isn't, that important relative to this. It's basically what Rincon went over of when two processes are demanding the same resources, and you need one to complete the other, and then it's a deadlock, right? But the process of solving these matrices is pretty simple. Q is going to be the example matrix, so this is going to be something that we're comparing to, and V is going to be the matrix that we're comparing Q to. So these are kind of going to be intertwined, I guess, and A will be useful in a second. So first off, whenever you're looking at this, we have so the thing is you need to look at these rows as processes, okay, or P. So in here, this is going to be represented as P1, and this will be P2, this will be P3, this will be P4, okay? So when they ask you, oh wait, that's cool. I could see when I hover over, that's kind of cool. So when they ask you, what processes are deadlocked, if they say like is P1 deadlocked, is P2 deadlocked, P3, whatever, that's from these rows here. okay? Okay. So let's go ahead and learn how to actually use the algorithm and solve this. So if you want to, there's actually a few ways you can do this, I learned, but the most simple way is in another review video that's in the Discord, where you can start by taking the first one, the first row, so in our case is 1, 0, 0, and you compare it to v. You compare it to your v vector here that you solved, whether you were given r or maybe they just give you v. And in this case, it's 1, 0, 2. Okay. All right. Now, if this here is bigger than this, then that means that this is a deadlock. Okay. And how you compare these matrices values, I guess, and we could write it like this if you wanted, is just number by number. So we take 1 and 1. Well, this is equal to. So let me write it like this. Greater than is a deadlock. Okay. Less than or equal to is safe. Okay. All right. I'm sorry. Yeah. That's correct. Okay. So in this case, 1 and 1, that is less than or equal to. So that's safe there. 0 and 0, that's less than or equal to. 0 and 2, that's less than or equal to. So this is safe. Okay. So this is safe. And now remember that this number here is P1. Okay. This is P1. So P1 is safe. This is not a deadlock. Okay. Now that's good because and keep in mind, when this is safe, when something is safe, and I'll write this down here, when safe, it is no longer going to be messed with, no matter what, no matter any circumstance, no matter how much further you get in the algorithm. When it's safe, it's done. You don't have to worry about it anymore. Okay. I think that confuses a lot of people because you'll see that we'll have to backtrack and stuff, but this is safe. And so when it's safe, you're done. So when safe, do not edit again. Okay. Now again, and I'll label this here. This is our Q, and this is our V. Okay. And let me write this up here, just so that this is actually. I'm gonna just select it here. Move that here, and move this here. Okay. All right. And then again, this is our Q vector, or Q matrices, sorry. And then this is our V matrices. Now, when it's safe, you still have to do some work, okay? When it's safe, what happens is that you have to take the allocation matrices corresponding to P. So, for instance, if this is P1, we can see here, and this is safe. Now, because this is a good process, this is good to go, we determine that there's enough space for this process to execute. Now we have to see how many resources is that going to take up, okay? And that's what our allocation is here, okay? This is labeled the exact same, P1, P2, P3, P4. So now, what we do is we take this vector, we take our V, and we update it. We change V. Because now the available resources have changed since this process here is executing, okay? So we take 1, 0, 2, and we add it to the corresponding A row of P. So if P1 is 1, 0, 0, then P1 here for the allocation is 0, 0, 2. And we add that. We add 0, 0, 2, okay? Now when we add that, we get 4, 0, and 1. This is our brand new V, okay? This is equal to V. So now, throughout the entire rest of our algorithm, throughout the rest of our workspace, this is what we're going to be using as V, okay? Does that make sense? So, again, you have to, I think a lot of people just look at the numbers and look at the math and think, well, you know, we'll do this and do this. Well, you have to look at it from a computer science perspective. These are actual processes using resources, right? And you're just given values of of how much resources they take, how much is available, and how much they cost, and the requirements, right? So it makes more sense that your resources available are changing when one process is actually using resources, okay? So that is why V changes. Now we take this V and what? Sorry, somebody have a question? Okay. Any questions so far? Any questions so far? None? Okay. All right. So now that our V is updated and we've determined that P1 is safe, we can move on now to P2. Okay. Also, somebody please mute your mic. Okay, I'm just gonna mute them. All right, there we go. Sorry. Okay, so now P2 is what we need to check next. All right, because your job is to verify all these columns here. So P2 is 2, 0, 3, right? Yes, I think so. Yeah, 2, 0, 3. Now this needs to be compared to 1, 0, 4. Okay. Is 2 less than or equal to 1? No, it's not. So instantly, this is deadlocked because this process takes up more than what we have available. Therefore, this is a deadlock. Okay. Now, it's important to keep in mind that there is a sequential order or a queue that you could call in which these processes need to be executed. So by default, and I'll just call this queue, by default, we have P1, P2, P3, and P4, right? And we started off here by solving P1, so that's crossed off. Okay, oops. So that's crossed off, right? P1 has been solved. And P1 is being removed because it's safe. And remember, when we say it's safe, we do not edit again. Now, P2 is deadlocked, okay? That doesn't mean that it gets removed. Instead, it gets pushed to the end of the queue. So that means that because P2 is deadlocked, we possibly might have to come back and check it again to re-verify if it's possible for it to be safe. Our goal is to get nothing in this queue. Our goal is to get everything out of this queue. But because P2 is deadlocked, we need to move it back up here because maybe in the future this might not be still deadlocked. Because if V can be changed, that means there's a possibility that P2 can also be safe, right? Because this is changing. So that is why in our imaginary queue here, we put P2 at the end. We don't erase it, okay? And I'll just rewrite this. So P3, P4, P2. Okay. So, all right, P2 is deadlocked. We understand that. And now we can go and look at our queue if you want. And we could say, all right, P3 now is, let me take a look at P3. It's 202. 202. Okay. Now, we can immediately look and see, well, compared to our V here, which is 104, which was edited, we can see that 2 is greater than 1. Therefore, that this process is also deadlocked. Okay. And now we can move it out of our queue, or to the end of our queue. Okay. And now we just need to do P4. Okay. So P4 here, and we'll say is 111, 111. Okay. Now 104 is equal to a deadlock. Okay, because if we check 1 and 1 is equal. We check 1 and 0. 1 is greater than 0. Therefore, that this is deadlocked. Okay. Now, this is it. That's it. These processes are deadlocked. P2, P3, P4, and P1 is safe. I'm going to do another example here in an instance where this wasn't deadlocked. But there is one final question that they're going to ask you, and it's going to ask you the final value for w, the w vector, w's. Now, if I'm not mistaken, w, I think, I'm going to be honest, I completely forgot about this until like last second. I think w is just your final v vector, okay? W should just be your final v at the end of everything, okay? And this is kind of just to verify that you didn't get lucky with your numbers, right? That v is also fully updated. So, and I think it's actually called w because you can put two v's next to each other and it's like a completion v. I don't know, but yeah. So that's what w is. So I'll write that up here, just so it's a little more. So you can take a picture of this, and w is equal to final v. Okay. All right, so that's it. This would be the solution to this problem. We found all the deadlocks. When you find all the deadlocks, there's nothing else you can do. But let's go ahead and do a quick sample. Let's assume that this here was a 0. Let's assume that P4 was a 0. I'll change that here. Okay. Now, that means that this is not safe. I mean, sorry, this is safe. So 1 is less than or equal to 1. 0 is less than or equal to 0. Oops, sorry. And 1 is less than or equal to 4. Therefore, this vector, P4, is safe. Okay. Again, what do we do after we find a safe vector? We take the allocation of the processes. In this case, it's 0, 0, 0. Again, because in this example, we're not really meant to be editing it, but I'm going to go ahead and change this here to 1, 2, 1. That's fine. So now we have that P4 is safe. This is safe. So now we take our allocation. So this is how much resources it's actually going to be using, 1, 2, and 1, and we add that to our V, right? So now 1, 2, and 1 is going to be added because this is P4. This is A sub P4. Okay. And we add them together and we get 2, 2, 5. Now this is probably, these are pretty high numbers. You probably won't get something like this, but I mean, it's still possible. So now this is our new V. Okay. Now we've, again, remember this rule here, when safe, we don't edit it again. It's good. So P4 is good. So now we can go up here and we can remove P4 from our queue. But you see there's still P2 and P3 left in our queue after we've been updating V. That means we need to take our brand new V and we need to go back and we need to check P2 and P3 again. Okay. So let's go ahead and let's compare P2 to 2, 0, 3. Okay. And we will compare that to 2, 2, and 5. Now 2 is less than or equal to 2. 0 is less than or equal to 3. 2 and 3 is less than or equal to 5. Therefore, now this is safe. Okay. Now because this is safe, what do we do now? We take the allocation of P2, the A vector, A sub P2, and we add that to our V. Okay. So now A sub P2, which is 1, 0, 0. Okay. So let's go ahead and do 1, 0, 0. And now our brand new V is 3, 2, and 5. Okay. And we can now erase it from our queue here. Last but not least, we have P3. Obviously, we can look at P3 here and just be like, yep, it's safe. But I'll write it down again just to make sure here. Okay, so P3 is 202. Okay, and we need to compare that to our brand new V, which is 325. Okay, and we see that it's less than or equal to our V. So now we go to A sub P3. We go ahead and add that. okay, which is 1, 1, 1. 1, 1, 1. And now our v is equal to 4, 3, and 6. And this is now safe. Okay. And now we can, of course, remove this from our queue. Now, are they all going to be safe? I'm going to tell you now, no. This is not a realistic example, but this is just, I'm just showing you what to do. That if you run into a safe, you have to, even if, let's say in this case, let's say 1 was deadlocked and 2 was safe, you need to still continue on 3 and 4 and then go back to 1. Okay? Because it's like a queue, right? So every time V is updated, make sure you go check your other ones that are deadlocked because they might have changed. That's what this example is saying. There's no, I am almost 99.9% sure all of them are not going to be safe. So, don't go in assuming that it's all going to work out like this, but this is just, again, another example. Now, they're going to ask again at the end, what's your W? Well, this was our final vector. After all of them are safe, there's no more things we can compare. So our W vector is going to be 4, 3, and 6. Okay? So, yeah, that's deadlock detection algorithm. Any questions or anything like that?
Will we be asked to provide the queue?
No. This is just for you to like help visualize, keep track of what processes you're working on. You don't have to queue. Yeah, no problem. Okay. Yeah. So. Yeah.
So, before you changed the question a bit,
Mm-hmm.
in A, P4 was 0, 0, 0.
Mm-hmm.
And you know how it was deadlocked, but for example, if they ask you which lines are deadlocked, do you include P4 in that? Or since the allocation vector of P4 was 0, 0, 0?
Oh, I see what you mean. Yeah. No. So again, it doesn't. The numbers. I mean, yeah. No, you wouldn't. This would still be deadlocked because no matter what the allocation is, it's how much Q takes. If Q is taking more than what we can allocate to it, then it's going to be deadlocked, right? If Q is taking more than what V can offer, what's available, then Q is going to be deadlocked. Okay, because if we, you're talking about this one here. Oh, I guess I changed it here. Yeah. So 0, 0, 0. I see what you mean. Yeah, no. So this is 0, 0, 0. So then this is just not changing, right? So this is saying 1, 0, 4. And so this would be safe. And then 1, 0, 4, we already compared 2 and 3 to 1, 0, 4. So this just happened to be 0, 0, 0. But because we compared 2 and 3 to 104, and it's still staying 104 even after this is safe, then you don't need to redo these here. Yeah.
But I think you also changed like the Q vector. I think it was 1, 2, 1. So in that case,
Yeah, I can.
more in between.
So this originally was 1, 1, 1.
Oh,
Mm-hmm.
so then if we go back down to like the answer,
Mm-hmm.
and it comes as like that dot,
Mm-hmm.
1, 0, 0.
Mm-hmm.
Because I saw an example earlier, and on that, on the last part, it was asking us to like to choose which, like there was like P1, P2, P3, P4, and it was asking us to like choose which ones are deadlocked. But in the answer, like for example in this one, P4 wasn't chosen, and apparently it's because the on the
Oh. Honestly, when I took this class and stuff, I've never seen anything about 000 meaning that it's deadlocked or not. Um, I could email Rincon actually and ask him before your exam. That's a good question. I don't think that this changes anything. But I can message him and then tell y'all on the Discord. I'm assuming you just do the process, like, you just run the algorithm and then 000 is just 000. But I mean, it's fully possible that this could imply that it's actually not deadlocked or something because it's not using any resources. That's a good question. Let me ask Rincon, okay, and then I'll message in the Discord about it. Yeah.
I want to see the example I was talking about. It's on the extra credit. Yeah.
Okay. Yeah, I can take a look. Do y'all want me to do another example fresh? I can.
Yes, please.
Okay.
Thank you.
Okay. Sure. Oh, I see this problem here. Okay. Let me save this image.
Do you think he'll give us something like that on extra credit or exam? Because it first confused me when I saw that too, since he never mentioned anything with the allocation matrix being zeros.
You want my honest answer?
That was a little question.
Honestly, I would I would be prepared for it. I'm gonna stop screen sharing real quick and alright. I go ahead, I went sent him a message there. Okay. Let me screen share again. Okay. This is the problem you're talking about, right?
Yeah.
I see what you mean. You say P4 is not deadlocked because it's 000. Yeah, okay. That's a good question.
Yeah, I believe he did went over in class. I believe he said that it is the case. That
Okay.
But yeah, I would like to make sure to go.
Okay. All right. Well, honestly, if this is how it is on the practice, he's probably gonna pull it out during the extra credit. So, I'll redo it this time. I'll follow that rule. Sorry if I confused you all with that. We didn't have that last semester, so I guess that makes sense.
No worries. The way I like to think of it is that there's no memory being allocated to that row of the matrix, so
It can't cause a deadlock, yeah.
Yeah.
That makes sense. That makes a lot of sense. Do you want to unserver deafen those people? I don't know if they're still like talking or something. I only muted them because
Oh, okay. I can see why.
yeah, that's why. So I don't know if they.
Can you put your mic on I can see why you
Okay. All right. Let's go ahead and do this. So, we are given V. That's nice. We don't have to solve for V. Let me see. I think Rincon. No, I'll get a notification if he responds. Okay. So, let's start off by I'm gonna label, because this is the raw question, right? I'm gonna label P1, P2, P3, and P4. P1, P2, P3, P4. And then this is for me personally. I'm gonna write my Q. Okay. I write my Q and we start with P1, P2, P3, P4. All right. So following this queue, we want to go ahead and compare the requested amount of memory, or I don't know, data, whatever you want to call it, and then the available given. So we have 3, sorry, let me write it like this. We have 3, 1, 2, and 0. And then we compare it to our available of 1, 0, 1, and 3. Okay. Is 3 less than or equal to 1? No. Boom. Deadlocked. I'm just going to put DL. Okay. Now, this is deadlocked, so P1 gets pushed back in our queue here. And, yeah, that's deadlocked for now. We can move on to process 2. So P2, we have 2, 1, 0, 1. And we compare that to 1, 0, 1, 3. And yeah, I'm just going to label this V. Like, I'm just going to say that all of these are V. Okay. So is 2 less than or equal to 1? Nope. So immediately this is also deadlocked. Okay. Let's go ahead and move this into the back of our queue. Again, queue is not required whatsoever. You don't have to do queue, but I think it's going to help you a lot if you do it. 1, 0, 1, 1, because we're going to compare P3 now, right? And we compare that to 1, 0, 1, and 3. Is 1 less than or equal to 1? Yes. Is 0 less than or equal to 0? Yes. Is 1 less than or equal to... Yep. All right. Cool. This is safe. Safe. Okay. Now, because it's safe immediately, I'm going to remove this from the queue. Okay. We're no longer going to be working with P3. Now, we need to take how much is that process actually going to use, or how is that going to add to the load of V? Okay. So go and look at our A. And let me label this a little nicer. Sorry about that. Okay. Okay. Now, we take 1, 0, 0, 1, and we add it to our vector. So A sub P3 is equal to 1, 0, 0, 1. And we need to go ahead and add this. I don't know why I keep saying vector. I mean, I think you understand, though, what I mean. It's not technically called a vector, though. And now, this is our new V. Okay. Nice. Now, we still need to continue in our queue. Okay. I know you might be tempted to take this V and go check 1 and 2, but we must follow the queue. Okay. So now, let's go ahead and take P4, which is 1, 2, 3, 4. And we compare that to our new V of 2, 0, 1, 4. Okay. Is 1 less than or equal to 2? Is 2 less than or equal to 0? No. Therefore, this is deadlocked. But, pause. But according to this unsung rule, because our allocation is 0, meaning that this is technically, while yes, the requested memory, data, whatever you want to call it, is a lot to bear, it's actually not using anything. So because our A sub P4 is 0, 0, 0, 0, we can actually claim that this is safe. Okay, so we can claim, how do I write this here? Let's write next here. Safe due to A of 0, 0, 0, 0. Okay. Now, another question, I guess, that I don't really have the answer to right now. Well, never mind. Dumb question. I was going to say, do we need to update the V? Of course not. It's 0, 0, 0. It's not going to make a difference. So, all right. Now, I guess that's the one little trick to this is understanding why P4 is safe, even though it violates the algorithm rule here. But because it's 0, 0, 0, we'll assume it's safe. which means that we can erase it from our Q up here, P4. And now P2 and P1 are all that's left. So now we take our updated matrix, which are, and we take 2, 0, 1, 4, and we compare it to P1 and P2. Okay? So P1 is our 3, 1, 2, 0. And we compare that to our most recent, and I'll star this because it's our most recent, is our 2, 0, 1, and 4. Okay. Is 3 less than or equal to 2? No. This is greater than. So this is still deadlocked. Okay. Now we can move this over. Okay. In fact, I'll just rewrite this here. Okay. Now we can compare our P2 to our brand new vector of 2, 1, 0, 1. And we compare that to 2, 0, 1, and 4. Is 2 less than or equal to 2? Uh-huh. Is 1 less than or equal to 0? No. That means this is greater than. This is also deadlocked. And now with nothing left, we can fully assume that P1 is deadlocked, P2 is deadlocked, P3 is safe, P4 is safe due to A sub P4 equaling 0, 0, 0, 0. And now, last but certainly not least, our W. Our W is our final V vector, the V vector that we ended with. In our case, it's our most recent one, right? 2, 0, 1, 4. And this should be your answer, assuming they don't ask for V or for R, okay? And again, remember that R is equal to V plus A. He could give you R, and he could not give you V, and then you use this to solve for R. Hopefully you know how to rearrange that and solve for V. But there you go. Any questions?
Quick question.
Oh man, wait, there's a whole chat. Okay, sorry. Yeah, whoever.
Yeah. So if that is true, then we can automatically just if we see 0, 0, 0, 0 on allocations, we can automatically just ignore having to compare P whatever.
Yeah, that looks fine to me. I mean, I would still do it just to like have like the order in your brain, but if you just want to look at it and be like, nope, that's safe, don't even worry about it, don't even compare, in fact, just erase it, go for it. Yeah, I don't see a problem with that because again, V is never changing, right? If A is 0, 0, 0, 0, V is, it's not going to change. So deadlocked or not, you know, the actual important part of the algorithm is never making a difference. So yeah, you can just brush it off if you'd like. And again, you can ask Rincon right before, obviously the whole class. I mean, there's an hour before you do the extra credit. You can ask him about this. He hasn't responded to me yet, but yeah, I'm assuming just to follow this rule just in case. Okay.
Yeah, I was gonna say in class when he did his slightly different, but the very second step was that whenever you have an allocation with zeros, he did stars for his to signify safeness.
Okay.
Just automatically started and then checked the rest of the remaining P's if they were less than or equal to. So I guess like
Sure.
that's the first step.
Yeah. Then yeah, go ahead and look at it like that. We say, okay, well, we see that Q is values, but oh, this is 0, 0, 0, so this is just safe. No matter what, this is safe. And you could just cross this off if you want and just work with P1, P2, P3 for the rest. If that's what you wanted to do. Yeah, that's fine. Sorry, I'm sorry in my first example I didn't go over that. I actually kind of had no idea about that. But it makes sense.
Last step we found that P2 is safe, would we then have to recheck P1?
P2 is not safe.
Yeah, but I'm saying if it was.
Yes. Mm-hmm. Yep. You'd have to go look at your queue again. See that, you know, let's say P2 is safe, we erase it. No, P1's still in our queue, and we got a brand new V. So yeah, go ahead and check it. Mm-hmm. Okay. Anything else? Any other questions? If y'all really want me to, I can do one more example, but I don't really think I have any other examples. Somebody might have to provide it for me because I don't have any on deck. But yeah. Remember, whatever you see on this, right? If this does end up being deadlock detection, which I'm pretty sure it might be, then you're going to have bankers on your exam. And if you have bankers on your extra credit, then you'll have deadlock on your exam. But at least now you should be well versed and perfected in the deadlock detection algorithm. Okay. You could look at it as anything left in the queue is also deadlocked if you wanted. You could just write deadlocks. But I don't know. Anyway. All right, well, if there's no other questions or anything, let me upload this YouTube video. Let me check the chat real quick. I see that's going off. I didn't know. Is EC going to be already deadlock, or did he already? No, I haven't done bankers. I'm just gonna have to like be legal here and say that I'm pretty sure you're gonna get deadlocked tomorrow. Okay. The recording will be posted. I'll post it everywhere. It'll be in resources. I'll put it in extra credit. It'll be in this Discord. No, I'm not going over bankers. No. Bankers isn't too bad. This is harder than bankers, in my opinion. So, yeah, bankers is really similar. Yeah, pretty much. Yeah. I'm a little rusty on bankers too. The only reason I'm going over deadlock is because, again, pretty sure that's what you're going to get tomorrow. So, and if not, I'm so sorry. But, yeah. You should still do the same process, even if you're given bankers. But y'all do fine tomorrow. If you're here, if you took the time and effort to be in this call, you're going to be just fine tomorrow. Plus the exams they get easier from the first exam. And you only got one programming question, which is semaphores, I think. I don't know if I should do a review on semaphores or not. I haven't decided yet, but bankers, you just find V, deadlock, you're finding, yeah. Okay. Yeah, I could probably do a review on semaphores. Those are a little confusing. Let me talk to Rincon, have him give me an example that I can give y'all, and then I'll probably go over it Wednesday then. I'll make an announcement if I do. But I'm gonna stop this recording. This is